All right, so how do we define momentum in the first place? What is momentum?
Mass times velocity.
Yeah. And since velocity is a vector, direction actually matters. That means momentum is also a vector. So velocity is a vector in the sense that it has a direction. You don't want to just say the object is moving at 5 meters per second. You want to say the object is moving at 5 meters per second to the northeast, or the object is moving at 5 meters per second upwards, or something like that. Velocity actually has a direction associated with it. You want to say which direction the object is moving. Does mass have a direction? Like, would we say this object has a mass of 5 kilograms to the east?
No.
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 Mass does not have a direction. Mass is what we call a scalar quantity in the sense that it has no direction associated with it. So velocity is definitely a vector. It has a direction. Direction matters. Whereas for mass, direction does not matter. There is no direction associated with the mass of an object. So mass would be called a scalar. And if you multiply a scalar times a vector, you get another vector which has the same direction. So momentum is a vector in the direction the object is moving, same direction as velocity. The scalar multiplier just modifies the magnitude, the size of the vector. So you might have an object that's moving in some direction. Let's say the velocity is 20 meters per second to the northeast. And let's say the object has a mass of 3 kilograms. If you multiply those together, what do you get?
60.
Yeah. And 60 what? What would be the units of measurement there?
Kilograms, meters per second.
Yeah, because we're multiplying kilograms times meters per second. So momentum would be 60 kilogram meters per second. And since momentum is a vector, we need to specify a direction also. Since we're just multiplying this vector by a scalar, we keep the same direction. We're just adjusting the magnitude. So this would be a vector that's 3 kilograms times as long. Although it doesn't really make much sense to directly compare these sizes because they're measuring different things. Meters per second and kilogram meters per second are not even the same unit of measurement. So although it's tempting to say that the momentum is 3 times as big as the velocity, it's really 3 kilograms times as big as the velocity. And 3 kilograms times as big doesn't mean it's literally 3 times as long. They're measuring different quantities, so it doesn't really make sense to draw them to scale with each other. But the momentum would definitely be in the same direction as the velocity. It would just have a different magnitude and different units of measurement. So the momentum is really describing not only how the object is moving, but also incorporates the mass of the object. And a very useful way to think about the mass of an object. How do you usually measure the mass of an object? Like if you want to know the mass of an object, what measurement would you take on it to determine that?
I want to say scale, but I feel like that's wrong because I think the scale takes into account gravity.
It does, and I mean, pragmatically it works. You can just take the scale here, like let's say you've got this object, it has some mass. You put it on a scale, and the scale is measuring the force of gravity. The scale is measuring how strongly gravity is pulling it down. So the scale measures most directly the force of gravity on the object. Although the force of gravity is proportional to mass. Force of gravity is mass times acceleration of gravity. And on Earth, about 9.8 meters per second squared. So if you know the force, you can find the mass just by dividing by gravity. So pragmatically, we usually indirectly measure the mass of the object by measuring the force of gravity on it and then dividing by g. But we should be able to find mass without any reference to gravity, because mass also does one other important thing. Let's say you would just push on an object. What would happen to it?
Moves.
Yeah, if it's not moving yet, then pushing on it makes it start moving. But what if it's already in motion? If you got an object that's already in motion and you push on it, what happens to it?
If the amount of force that you push it in is proportional to already the speed that it's going in, then it'll either continue to stay in motion unless there's friction. But if it's not, like if you push it harder, okay, so if you push it harder or harder than the velocity it already had, it would make it move faster.
Well, keep in mind we can't directly compare force and velocity. They're different quantities. They've got different units of measurement entirely. So we can't really say the force is more than the velocity or less than the velocity. But we can certainly talk about direction. If you push on the object in the direction it's already moving, what would happen to its motion?
It'll move farther.
Yeah. You increase the velocity. I wouldn't necessarily say moving farther because the distance it travels is also going to depend on how much time passes. But it would certainly be moving faster. The object's already moving and you push it in the direction it's moving, you increase its speed and make it move faster. So the force causes a change to the velocity. Or if you push it in the opposite direction, if it's moving one way and you push it the other way, you're going to slow it down. Or if it's moving one way and you push it a completely different direction, you're going to change the path it's traveling on, which also counts as changing velocity because velocity includes direction. So like if an object is moving 10 meters per second to the north and you make it curve so it's moving 10 meters per second to the east, that counts as a change in velocity because you've changed the direction, even though the speed it's traveling at hasn't changed. So generally a force causes the velocity to change. And what do we call how quickly the velocity changes?
Acceleration.
Right, acceleration. So force causes acceleration. And those are directly proportional to each other. The amount of force is proportional to the amount of acceleration. For instance, if you apply a certain amount of force to an object and you make it accelerate, and then you try applying 3 times as much force, you'll find that it accelerates 3 times as much. Also, these count as vectors because direction actually matters here. So that means we should be able to write force as being equal to something times acceleration. And what is that something?
Mass.
What determines, yeah, this is mass. That determines how much force you need. And I guess this should really be the net force in the sense of the total of all the forces acting on it. If you've got several forces, this should be the sum of all of those forces added together, the total or net force acting on the object. But this really means that you apply a force or some forces to the object, and the object is going to accelerate. It's going to accelerate in the direction of the total force. And that doesn't necessarily mean it's going to move in that direction. It just means it's going to change its motion in the direction of the total force. And mass is the constant of proportionality, which means if an object has more mass, if you've got a very massive object, what does that tell you based on this formula?
If the mass is greater as opposed to like something with less mass, you need more acceleration to move it just as far.
Well, the acceleration is multiplied by the mass to get what?
Force.
So let's say you want a certain amount of acceleration. You want the object to accelerate at, let's say, 3 meters per second squared. If the object is very massive, what do you have to do to it to make it accelerate at that rate?
Accelerate it more.
Well, we want it to accelerate at a certain rate. What do you have to do to cause that acceleration?
So does it need more force?
Yeah, more mass means you need more force to get the same result. So mass could be thought of as a level of difficulty. Mass is a measure of how much effort it takes, how much force you need to get it to accelerate at a certain rate. So more massive means it's more difficult to change the velocity. Not just for it to be moving, because it could be maybe it's already in motion. But forces don't cause motion. Forces cause change in motion. So if an object is moving at a certain speed, which might be 0 or might be non-zero, if you want to change its motion, the more massive it is, the more force is required to cause a certain change. Or an object with very small mass is very easy to change its motion. You just give it a little tap and you send it way off in some direction. But generally, mass could be thought of as a level of difficulty. More massive means more difficult to change the motion. Any questions on the meaning of that so far? And note that this provides an alternate way of measuring the mass. Here on Earth, we typically measure the mass just by putting it on a scale, measuring the force of gravity and dividing by g, the acceleration of gravity. But you could also measure mass by pushing on the object, measuring how much force you're applying and how much it accelerates as a result, and divide those. The amount of force you apply in total divided by the acceleration that it experiences as a result is also the amount of mass. So even if there's no gravity, if you're just on some space station and gravity is not something you can really use, you can still measure the mass of an object, or at least get a pretty good estimate, by applying a force to it, observing how much it accelerates as a result. And if it takes more force to get it to accelerate, that means more massive. So you could at least compare the mass of, like, let's say you've got two unlabeled boxes and you know one of them is large mass, the other one's small mass. Push on both of them. Whichever one requires more force to make it accelerate a certain amount is the more massive one. If we take that back to the idea of momentum, momentum is a measure of both the motion of the object and how difficult it is to change that motion. Since mass is just the difficulty level, how difficult it is to change the motion, momentum combines both of those. Description of how the object is moving, including both speed and direction, multiplied by a measure of how difficult it is to change that motion. Any questions on that so far? And of course, this means that the momentum of an object, like let's say you have an object with very large momentum. An object with very large momentum might mean that it's a small object moving very fast, or it might be a very massive object moving very slow, or maybe somewhere in between, a medium mass and a medium velocity. But any combination of those could have the same momentum as long as those multiply to the same value. Any questions on the meaning of that so far? So let's say we want to change the momentum of the object.
This question is kind of like off topic, but I guess like a conservation of momentum, does that mean that that the momentum has to equal 0?
Well, conservation of a quantity just means that quantity doesn't change. So we wouldn't say momentum equals 0. We would say delta momentum equals 0.
Oh, okay.
And since that's all about change, that actually ties in very closely to this idea of how do you change momentum. Because I mean, this is basically looking into when would we expect momentum to be conserved versus when would we expect momentum to change. If you've got an object that's moving with a certain amount of momentum, what do you have to do to the object to change its momentum?
I mean, logically, only change its speed, but I feel like there are cases where the mass could be changing. Like, for example, like I was thinking like a rocket or something where you're going to run out of fuel. So then technically the mass would be changing too.
Yeah, there are some cases where the mass is changing. Like as you said, with the rocket, as it burns fuel, what's left in the rocket is now more or less and less massive because it's expelled some of the fuel out the back as exhaust. Another example that shows up from time to time is conveyor belts. If you've got a conveyor belt, the conveyor belt is moving at a constant speed, but if you push a box onto this conveyor belt, the conveyor belt is now carrying more mass. But in most of the cases we're going to be looking at in this class, we just have an object that doesn't change its mass. You've just got this object that's moving, its mass is staying constant. So the only part that could be changing would be what?
Velocity.
Yeah, velocity could be changing. And how do you make the object change its velocity? What do you have to do to the object to change? And note that this is vectors. So change in velocity might mean you change how fast it's moving, or you could be changing which direction it's traveling, or both. Either or both of those could be changing. So how do you make its velocity change? What do you have to do to the object to change how fast it's moving or change which direction it's traveling?
Add an external force.
Yeah, you've got to apply a force to it. How do you change momentum? Apply a force. And for this, we can bring in the idea of net force equals mass times acceleration that we saw earlier. In fact, if we just start there, force equals mass times acceleration. Anyone know how we define acceleration in the first place?
Can you repeat the question?
Yeah. Sorry, what was that?
What did you say? Define acceleration as what?
In the first place, what is acceleration?
It's the change in velocity.
Yeah. Specifically, change in velocity as time passes. The ratio of how, essentially it's describing how fast the velocity is changing. The ratio of how much the velocity is changing versus how much time it takes to do so. So large acceleration means you're changing velocity very quickly. Small acceleration means you're changing velocity very slowly. No acceleration means velocity is not changing as time passes. And since velocity is a vector, that means acceleration is also a vector. More accurately, you could say acceleration is the derivative of velocity as time passes. But if we're talking about a short amount of time, you could just say it's the amount that velocity changes divided by the amount of time that passes. If we substitute that in here, we get force equals mass times change in velocity over change in time, since that's what acceleration is. But if we combine these in a different way, if we group together the mass times the change in velocity, what do we call mass times change in velocity?
Momentum.
Yeah, mass times velocity is momentum. So mass times change in velocity is change in momentum. And this is if we assume that mass is constant. If the mass is changing, this becomes different. We'd have to consider the delta mass also. But as long as the mass is constant, change in momentum is mass times change in velocity. So if we make that substitution, we get force equals change in momentum over change in time. Or again, more accurately, the derivative of momentum. The amount of force being applied to the object is the derivative of momentum, the rate of change in momentum, how fast the momentum is changing. And this is just another way of writing this idea of force equals mass times acceleration. In fact, even though modern physics textbooks usually write it as force equals mass times acceleration, Newton apparently first wrote this as force equals the derivative of momentum, which is true, and also because he had just invented calculus and wanted to define everything as derivatives. So if force is change in momentum over change in time, then we could also think of this in terms of this is how you change the momentum. You apply a force to the object, and the amount of force tells you how quickly the momentum is changing. In fact, you could also solve this for change in momentum. How would you isolate change in momentum here?
Force times delta t.
Yeah. The amount of force being applied times delta t, which you could interpret as the amount of time the force lasts, the amount of time the force is being applied for. And this is called the idea of impulse. An impulse just means a force applied to an object for some amount of time. And specifically, you calculate it as the amount of force times the amount of time. What that does is it changes the momentum of the object. So and I guess more formally, an impulse is any force times the amount of time the force lasts. The actual change in momentum of the object is the total of all those impulses. So change in momentum, and we usually write impulse as J, lowercase j.
So impulse is like an extra force on like whatever object is moving?
Specifically a force applied for some amount of time. So an impulse isn't just a force. An impulse is the amount of force times the amount of time the force lasts. So this J vector, the impulse, is the amount of force times how much time it lasts. So this is how we define impulse. And an impulse causes a change in momentum, although it's really the total of all the impulses. The change in momentum of the object is the sum of all of the impulses acting on that object. So maybe if you just have one force acting on the object for a certain amount of time, then that force times that time is the change in momentum. But maybe you've got several forces acting on the object, and maybe each one lasts for a different amount of time. What you would do is you'd multiply force times time for each one of those impulses, and then add all the impulses together as vectors, and that tells you the actual change in momentum of the object. But if you're just dealing with one force, you don't need to worry about adding them together. You just have a force times an amount of time, and that tells you the change in momentum. But more generally, the change in momentum is the sum of all impulses acting on the object. Any other questions on that so far? So what if there are no forces acting on the object at all? If the force is 0, what does that tell you?
There's no impulse.
There's no impulse. And no impulse means what's happening to the object?
It's staying like at a constant speed.
Yeah. Or not necessarily a constant speed, but more broadly, a constant momentum.
Yeah, constant momentum.
That, assuming the mass is constant momentum means not only is it moving at a constant speed, it's also continuing in the same direction. Since velocity is how fast it's going and what direction it's traveling, constant momentum means that it's continuing in a straight line in the same direction. No change to the direction of its path or the speed of its motion. So if there's no force, or if there are forces, but they cancel out, that means no change in momentum. The object's momentum stays the same if and only if there's no total force acting on it. And this is usually called Newton's first law. Newton's first law is there's no force acting on an object if and only if there's no change in momentum. Which would mean either the object is staying still, momentum is 0 and stays at 0, or the object is moving, but it's moving in a consistent way. It's moving in a straight line without changing its speed. So that would be an object with no forces acting on it, or maybe there are forces, but they all cancel out, so the total force is 0. And this goes both ways. If you know an object's momentum is not changing, then you know for sure that the total force on it is 0. And if you know that the total force on an object is 0, then you know its momentum does not change. Any other questions on that so far? And this is where we get the idea of conservation of momentum. Momentum is conserved, that is, does not change, if and only if there's no forces acting on the object. And we can also extend this not only for one object, but for a collection of objects as well. If you have a system of several objects, maybe you've got several objects interacting with each other. The classic example is you just got 2 rocks that are crashing into each other. So let's say you've got rock number 1, whose mass is 3 kilograms, and rock number 2, whose mass is, let's say, 9 kilograms. And let's say they're moving at different speeds. Maybe one of them is moving to the right at speed, an initial speed, or I should say an initial velocity, since direction matters here, of, let's say, 10 meters per second. And the other one is moving to the left at an initial speed of 5 meters per second. Then if we look at each of these rocks individually as they crash, during the crash, are there any forces acting on the objects? Are they interacting with each other?
Yes, I think like if you drew a force diagram for rock 1, you would say the force of rock 2 is one of the forces.
Yeah, they're exerting forces on each other. During the impact itself, like before the impact, there's no forces at all, assuming these are far away from any planets. So there's no, let's assume they're just out in deep space. So there's no force of gravity, no atmospheric drag, no force of friction from the ground or anything like that. They're just drifting in open space. So while they're just drifting, there's no forces at all. During the collision, the two rocks are exerting forces on each other. So if rock 1 crashes into rock 2, rock 1 experiences a force to the left from rock 2 experiences a force to the right from rock 1. So they're experiencing forces from each other, which means individually they do change momentum. Each rock is experiencing a force, so each rock changes its own momentum. But if you look at the whole system, if you treat both rocks as just one big extended object, are there any forces from anywhere else acting on the rocks?
Other than the force of gravity and normal force, which would cancel each other out, I'm going to say no.
Right. Yeah, I mean, if they were, like, let's say they were sliding on very smooth surface. There's no friction. They're being pulled into the surface by gravity, but the normal force, the push from the surface, is pushing them up. So those would cancel out. Or if these are out in deep space far away from a planet, there wouldn't even be those forces. So there would be no forces at all. So there's no external forces. During the collision, they're exerting forces on each other, but we would consider those internal forces in the sense that they're just objects in the system interacting with each other. If there's no forces from somewhere else acting on these rocks, we would consider this a closed system. So this is a closed system. There are no external forces involved. In the sense that the rocks could be interacting with each other. So the rock 1 exerts a force on rock 2 exerts a force on rock 1, but they're not interacting with anything else outside the system. So even though the individual momenta of the rocks individually is changing, we would say the total momentum of the whole system is conserved. In other words, delta P total is 0. That doesn't mean that the momentum is 0. It just means that the momentum does not change. The change in the momentum is no change. And we usually write this 0 with a vector sign also, because we don't mean the number 0. We mean a vector whose magnitude is 0. Any questions on that so far? So let's set this up as a momentum chart and try actually analyzing it. See if we can figure out, and usually what we care about is what's going on after the collision. Like here, we know everything there is to know about what's happening before the collision. We know both masses, we know both initial velocities. Let's say we want to know what happens after they crash. And usually in this class, we're going to use a tool called a momentum chart to keep track of all this. Because there's a lot of information to keep track of, and it's important to keep it organized. This particular chart is not strictly necessary. You could just set it up as an equation, but this momentum chart is a very convenient tool for keeping track of all the information. What we're going to look at is and we care about the initial momentum, the final momentum, and also the change in momentum for each object. So the columns we're going to use are initial momentum, change in momentum, and final momentum. And we're going to have a row for each object. So we'll have a row for rock number 1, a row for rock number 2, and also a row for total, because we care about the total momentum of the system. And let's fill in the values we know so far. Of these, what can we calculate right away?
The initial of each of the rocks.
Yeah, we can find the initial momentum of each rock just by multiplying mass times velocity. So for instance, for rock 1, we multiply 3 times 10, we get 30. Although since direction matters, we should specify 30 to the right, which we usually do by just drawing an arrow. So 30 to the right. And what about for rock number 2?
45 to the left.
Yeah, 9 times 5 would be 45 to the left. And you want to draw these to scale if possible. So this should be about time and a half as large. Also, what would be the units of measurement for all of these?
Kilograms, meters per second.
Yeah, because we're multiplying kilograms times meters per second. Since they're all the same units of measurement, I'm not going to bother writing it out on everything. I'm just going to make a little note up here just to remind myself that the units are kilogram meters per second for all of these. And then we could even add those to find the total. Can we just add 30 plus 45 to get 75 here?
Yes.
It's
not just numbers though. Vectors have direction.
Would it be like 15 in the other direction? Like,
yeah. And usually the way I think of adding vectors, if you imagine you just got a coordinate system, let's say an XY plane. If you start at the origin, just as a reference point, and you go 30 to the right, but then you've got to think of that as your new starting point. When you're adding vectors, you can imagine you're just traveling this far in this direction, and then from there as your new starting point, you're now traveling this far in this direction. So from this new starting point, you travel 45 in this direction. The total, the actual vector we're looking for is from the original starting point to the end of the last vector. So from the start of the first vector to the end of the last vector. And how far would that be? If you go 30 to the east and then 45 to the west, what's your actual distance from your starting point?
15 to the west.
Exactly, 15 to the west. And I find it's useful to think of this as if it were like giving directions for traveling. These vectors, of course, don't actually represent distances, they represent momentums. But the idea of adding vectors works the same no matter what type of vectors they are. So if you imagine this as like, let's say somebody tells you, go 30 kilometers to the east, and then go 45 kilometers to the west. In total, you've just traveled 15 kilometers to the west of where you started. So these vectors added together have a total of 15 to the west, or to the left, or whatever you want to call that direction. So the total momentum is just 15 to the left. In fact, since all this is one-dimensional, it's all just along one straight line, you could even think of to the right as the positive direction, to the left as the negative direction. So you could think of this as 30 plus negative 45, and you end up with negative 15. But if we're talking about the magnitude, we always treat magnitude as absolute value anyway. So this is not negative 15, this is 15 to the left.
I have a
Any
question.
questions on that so far?
Why did we start the 45 arrow at the end of the 30 arrow?
This is ultimately just the way we add vectors together. The idea is you're accumulating, if you're adding vectors together, you're accumulating the amount as you go along. So 30 means go 30 to the, or 30 to the right means from the starting point, go 30 to the right. If you want to add another vector, adding the vectors means you're trying to accumulate their effects. So from where you left off, then you go 45 to the left because you're adding these together.
Oh, okay, got it.
It's sort of a sequential thing. You're building up the effects as you go along. So you got 30 to the right, and then from there you attach onto it 45 more to the left. Any other questions on that so far? And this is also true even if you're talking about vectors that are not along a straight line. Like let's say you've got a vector, let's say we call this vector A, and we call this vector B. If you want to add A plus B, vector A plus vector B, then from some starting point, let's say the origin of your coordinate system. From the origin, you follow vector A, And then you treat where you've left off as your new starting point. From there, you follow vector B. So vector A plus vector B, and then the result, the actual sum of those, is just a straight line vector from your original starting point to your ending point. So this vector would be vector A plus B. And again, I find it useful to think of this in terms of distance. If somebody tells you travel this far to the northeast and then travel this far to the east, you end up at a location that's just this far from your starting point. So A plus B is basically how far you are from your starting point if you follow those directions, including which direction you go from starting point directly to the finish. So geometrically, that's how you would add vectors. It's usually described as putting them together head to tail, but it really just means that where you end off from one vector is where you start the next vector, if you think of these as how far you're traveling, including direction. Any other questions on that so far? And again, you can get a lot more practice on that if you take a look at the trigonometry review worksheet and the vector review worksheet I put up on mathandcheese.org. And feel free to bring those into office hours if you need some help with that. But let's see if we can finish off this momentum chart. If we're assuming these rocks are only interacting with each other, what should be the total change in momentum? Is the momentum changing, the total momentum, if they're only interacting?
Zero, right?
Yeah, so that should be 0. The total momentum does not change if the objects are only interacting with each other within the system. This is exactly what we mean by conservation of momentum, that the total is not changing in a closed system, which means final will be the same as initial. So we know after the collision, the total final momentum is also 15 kilogram meters per second to the left. However, that doesn't really have enough information to tell us how it splits up. Maybe one of the rocks comes to a complete stop and the other one has 15 kilogram meters per second of momentum. Or maybe they bounce off of each other with the same speed as each other. Or maybe they stick together or something like that. Or maybe we know how fast one of them's going and we don't know about the other. So there's still not enough information here. If all you know is the initial conditions, that tells you what the final total is, but doesn't tell you how it splits up. We've just got 2 values that have to add up to 15 to the left. So we need one more piece of information to finish it off. And let's say we have that piece of information. Let's say what we know is during the collision, they stick together. So let's say this is the before situation. Before the collision, the initial situation. And let's say the final situation is the rocks stick together. We're still going to treat them as if they're 2 objects that just happen to be moving together. But if we know that these objects are stuck together, what has to be the same about them?
The velocity and mass.
Yeah. If these objects stick together, and of course this doesn't always happen. Let's just say we happen to know in this situation that the rocks stick together. So that means that their V finals are the same. Because if their V finals were not the same, they'd be drifting apart from each other and not sticking together. Anytime 2 objects are moving together, they have to have the same velocity. Does that mean they have the same momentum?
No.
No, because the mass is like different.
Exactly. They have different masses, so their momentums will not be the same. But we know their momentums have to add up to 15. We've got M1 times V final. We've got M2 times V final. Those together have to add up to 15 to the left. So if we actually write that out as an equation, if we just write out M1 times V final, and we know M1 is 3 kilograms, plus M2 times V final, which is 9 kilograms times V final, and those have to add up to 15 to the left. We can actually combine these. The fact that it has the same final velocity means we can combine those and get what? What would be 3v final plus 9v final?
12v final.
Yeah, we can just combine like terms there, factor out a v final, we get 3 plus 9, so 12v final equals 15 to the left. And then how would we isolate v final?
15 divided by 12.
Yeah, divide both sides by 12. And dividing by 12 is going to change the magnitude, but it won't change the direction. So it's still going to be a vector to the left, but the magnitude will be 15 over 12. 15 over 12 reduces to what, 5 over 4? Or 1.25. So that means the final situation is going to be this lump of rock, 12 kilograms, moving at a speed of 1.25 meters per second to the left. So we now know the final velocity, and we can actually find each individual final momentum by just multiplying it out. 3 kilograms times 1.25 tells you this final momentum. 9 kilograms times 1.25 tells you this final momentum. Then you could add those together and make sure they really do add up to 15 to the left. And you could also fill in the changes by taking final minus initial for each one. And as one final verification, add up those changes, make sure they add up to 0. The changes can also tell you more important information about the system, like how much force each one experiences individually. The force of rock 1 on rock 2, the force of rock 2 on rock 1. Any other questions on that? All right, then that's about it for today. Try out those vector practice review worksheet and trigonometry practice review worksheet. Those are going to become very important when we've got vectors pointing in different directions in 2 dimensions. So give those a try, and I will see you next time.